So welcome to the last part of lecture 20 for Math 2R03. We've been talking about generalized eigenvalues. And so in this last part, I want to introduce the generalized eigenspace. All right. So first you have an operator and you have an eigenvalue. And then the generalized eigenspace of T is now defined to be the set of all generalized eigenvectors, right? So this is all the V such that t minus lambda I raised to the power of j evaluated at v is equal to 0 for some integer j greater than or equal to 1. So this is the generalized eigenspace. So the question then is, how does one compute this? Because this looks a little tricky, right? Because it seems more of an existence type of definition. Because in order to compute it, if I give you a vector, you have to say, well, I look at the first power, and does it vanish at the first power? Yes or no. Then you have to look at the second power. Then you have to look at the third power, and so on. So it doesn't seem like at the beginning like there'd be any way of computing this, because how would you know that you've done enough powers before you've seen all the generalized eigenvectors? Luckily, we have a theorem that comes to our aid, which kind of shows that you only have to really do one computation. So the generalized eigenspace of the eigenvalue lambda is the null space of the operator t minus lambda I raised to the dimension of v. Right? So this is great because over here you can compute this. You're only looking at the null space of one particular operator. And when you do that, then you get your whole generalized eigenspace. And let me give you a proof why this is true. Okay, so by definition, the null space of t minus lambda I to the dimension of v has to be inside of the general eigenspace, right? Because I can take the j to be the dimension of v. Anything that's killed by this operator would automatically be in the generalized eigenspace. So what we need to do is show the reverse. If I take anything in here, I can show that it's in this null space. Okay, so let's take a vector in the generalized eigenspace. Right? Well, that means then v is in the null space of t minus lambda I to the j for some j greater than or equal to 1. Now, if this j is between 1 and the dimension of v, then since the null space of t minus lambda ij is contained inside of the null space of t minus lambda I dimension v, that's kind of going back to all those lemmas that we had at the beginning. Here, I'll put that here. By lemma 1, we have v is in the null space of t minus lambda I dimension v. Okay, so that part's good. On the other hand, let's say that j is strictly bigger than the dimension of v, right? So v, we don't know anything about this j. It could be bigger than the dimension of v. But then v, which is in the null space of t minus lambda I to the j, it also has to be in the null space of t minus lambda I to the dimension of v by lemma 3. Because remember, it says that by the time you get to the dimension of v, you've stabilized. And that's actually enough to finish off the proof, right? Because what we have is, so v is in the null space of t minus lambda I raised to the dimension of v. So that kind of shows here that it is quite easy to compute the generalized eigenspace. It's really just a null space of a particular operator. So you find the eigenvalue, you know the dimension, you look at the operator t minus lambda I raised to the dimension of v, and you compute its null space. Okay, so to finish off our lectures for today, let's take the operator that we've been looking at kind of in today's lecture, the operator that takes the pair xy to y0, and we look at lambda equals 0. By definition, the generalized eigenspace of 0 of the linear operator t is, by the previous theorem, is the null space of t minus 0I squared, which is the same thing as the null space of t squared, which we just proved or computed in the example before the break. And let me just go back. Right here, we computed it, that it's equal to the whole space. Okay, so that kind of finishes up everything that we wanted to do today. So the big things that we've learned today are the properties of the subspaces, the null space of t to the k as we change the value of k. We've learned about generalized eigenvectors, and we've also learned about the generalized eigenspace g lambda t. So we'll pick up from this next class, and the idea is now we want to break the vector space in terms of these generalized eigenspaces. So that's enough for today. I'll see you in tomorrow's lecture.